Okay, let's get started. There should be much more people. I don't know. Anyway, let's get started. So today we'll keep talking about buffer overflow. Before that, you did the homework Crack Me level 1, and I want to walk through that. So let's say, how do you approach a hacking puzzle like this? So whenever you have a program, obviously you can do static analysis and dynamic analysis. Static analysis means you do not run the program. Dynamic analysis means you run the program and somehow analyze it. For example, the Crack Me 1, so how I will approach it is first I will just run this program to get a feeling what this program does. For example, when I just run this program, it looks like it doesn't do anything, right? I will try to give it some inputs there to say if it does anything. Still no, okay? Then after that, I will use other tools like strace, ltrace. Strace tells you what kind of system call this program makes. Ltrace tells what kind of library calls this program makes. So let's do ltrace. So ltrace is for library, then we just do something, and it actually calls two library functions. Here, it calls the library string length, and it checks the length of CSE security. And also, this is my input. It checks the strength of that. So probably you can guess. Maybe it's asking me to give a string which is CSE security, right? So maybe like that. Maybe I will just try that. Unfortunately, it's not the case. The program is slightly more complicated than that. So what else we can do is we can do some static analysis. You can download this program by clicking this button, the third button here. You can download the binary. So now I downloaded the binary, which is in our local machine. Then you can throw that in your whatever binary analysis tool. You can use obj dump in the terminal, or you can use more advanced tools. So today I want to introduce you to another tool called Decompiler. So Decompiler will not only translate machine code to disassembly, it will also translate disassembly to C code. So sometimes the program is really big. Reading disassembly or assembly is really difficult, right? So you hope there is a tool to help you translate to C code to help you better understand. And there are a lot of decompilers out there. IDA-Pro has a decompiler, but it's not free. Ghidra, the one developed by NSA, they have a decompiler. But if you do not want to install those, you can just use Binary Ninja, which is online. There is a Binary Ninja cloud version. You need to create an account there, but it's free. So here, let's just log into Binary Ninja, and I will upload that file we just downloaded, which is this one. Okay, then you just, let me set this as private. Then just continue. So it runs binary analysis, and you will say something familiar. Looks like what obj dump gives you. Those are binary, right? So there are some keys you should remember. So here you can only show those functions. Left-hand side, you have many different functions. If you click one of the functions and click the space bar, what you get is a flat view of this program from the beginning to the end. So here you can set what kind of information you want to show here. You can show address. You can also show opcode. And then you can say, let's say, where is the main function? Here's the main function. Then you can see the whole main function. This is almost the same as obj dump. So this is not the decompiler part. So how do you get the decompiler is you click the fourth tab here, the linear disassembly. You click the high-level IL. So this is a high-level intermediate language. It's pretty close to C. You click this, it will try to generate a C-like program for you out of the binary directly. So previously, you were looking at this huge, well, not huge, this big piece of binary code. Very difficult to understand, but if you look at the C code, it's much easier for you to understand. So throughout the semester, you probably want to look at the binary code, the disassembly, and also C code. Okay? Because as long as it changes to C code, it loses some information there. Some information you only find in binary code, the disassembly. That's why you probably want to use both of them. So let's take a look at here. This is the main function, and this is the prototype all of you are familiar with. This is a standard C prototype. The main function has argc, which is argument number, then argv, and also environment variables. Both of them are 2-degree pointers. Then after that, let's say there is a return address. Obviously, this one is not really referred here. Here, what do we have? We have this one. So what you can do with those kinds of decompiler is you can change the name of the variables. For example, here we have this variable is assigned to itself +1. You can change the name, you can change also the type. So this looks a little bit weird. This one probably tells you that this should be an integer. But the decompiler thinks this is a pointer, okay? Because the decompiler doesn't really do a very good job. What you can do is you can change it. You can change the type, click the type, then you can change the name. I will change the name to maybe a counter. Then instead of a void star, I will just change it to int, because I guess it's int. Then the decompiler will do the calculation again, do the analysis again, and now this is what we have. So that we have a counter. Because also here, we are using this to compare this value to the return value of stringness. Stringness is an integer, right? So it doesn't really matter, it doesn't make sense to compare a pointer to a stringness, to an integer. So this is probably an integer. Then you can say we compare this if the counter starts with 0. If eventually it gets longer than stringness, then we actually also compare here. So here, what do we say? We have the P. P is your input. No, P is not your input. If you click P, you can find the string here, which is CSE security, actually. How do I get back? I click main here. Let's see. So you can see the comparison is actually in this line. So this line is, this P is that hard-coded string, CSE security. And the counter is more like an index to that string. Then that string +1, we compare that, the program compares if that character is the same as your input with the same index. So basically, the key to this one would be CSE security, each character +1. So if you go back to the program here, CSE security, right? Security. Each one +1, so C would become D, S would become B. T, E will be F. S will be T. What's that? Where am I? Another E? Another E, right? So F, then C, D, V, I, J, T. What is after T? U? Z? Like this. So if you input this, maybe, yeah, then it will give you the flag. Okay? So this is a very simple crack me. There will be more difficult, more complicated ones in the future weeks. So you see, this is how you approach it. You don't have the source code, but you can get the disassembly. You can run the program. You can use strace, ltrace to run the program, so you can get a feeling what this program does. You can read the disassembly. You can even decompile the code. Worst case, if all the program is really too complicated, those approaches still doesn't give you what you want, then you can still debug the program, give it different input, and try to debug step by step to say what this program does. Okay, so let's move on. So last week, we started talking about stack-based buffer overflow. We talked about the history of buffer overflow, the information a C program needs to run. We talk about the C calling conventions, 32-bit and 64-bit. 32-bit, we mostly use a stack to pass the parameters. 64-bit, we use 6 registers to do that. If there are more parameters, we use a stack. We talked about how to overflow local variables. Today, in the in-class exercise, there will be a lot of challenge for you to overflow local variables, but it will be a little bit more complicated. So today, we will talk about how to not only overflow the local variables, we are going to overflow the control information on the stack, not the data, but the control information. And one piece of the most important control information on the stack is the return address. That tells the program where it should return to after executing this program, where should the control flow go. So it's a very important piece of control information. So we can override that, and we can change that, so we can hijack the program. We are going to use a lot of several complicated cases, how we can even chain multiple functions together, or we can call functions with many different parameters. So this will be our first control flow hijacking attack. What we saw last week, we were not hijacking any control flow. The control flow was intact in that case. So to hijack control flow, we are going to overwrite the return address because the return address eventually at some point will be used, popped, or restored into the EIP. The EIP is a register, or RIP, that's a register, tell the CPU where is the code next to be executed. Also, actually, there is another very important information is the stack pointer. It's also on stack, right? So by overwriting the the frame pointer, stack pointer, we can indirectly change the return address. Today, we're not going to talk about that. It's a more advanced attack, a little bit more complicated case. We'll talk about that maybe next week. So when, like say 20 years ago, those information, save the EBP or save the EIP return address, they were not really protected. So modern programs, when you compile modern programs, the compiler will insert some protection there. That's why so far the vulnerable programs I'm showing you we're using, I gave the compiler some specific instructions. Do not insert those protections. But later we will say even if the compiler inserts those instructions to protect the program, we can still bypass them. There are still approaches we can crack those programs. So in this type of attack, to overwrite the return address, the attacker's goal is just to change the return address. And we change the return address to the attacker's own code. The attacker may insert some code there. So this is called code injection attack. We may somehow inject some binary code in the address space, then trick the program, the CPU, to execute code from there. So this is one of the most common vulnerabilities in C and C++ programs. Because we have return address on the stack. We have other code pointers in C++. You can use code pointers to point to functions. So all the code pointers, as long as you override that, some point, those code pointers are used, then you execute your program. Especially C++ programs, those object-oriented designs, every C++ object, at the beginning of that, there is something called a V table, a virtual table. Virtual table is basically an array of code pointers, point to different member functions of the C++ class. Okay, so we are going to, let's say, look at our very first example program. Very simple program. The main function print out. So this program, there is a include. It is include the print flag header. I didn't include it here. Anyway, so this program will first print out the print flag function, where the print flag function it is, just to help you. Then you will call the vulnerable function, then call ipt the full. Okay? So the vulnerable function has a local variable buffer, 6 bytes at SQL level, not necessarily 6 bytes at binary level. That's why we need to look at the disassembly code to really figure out how much space the compiler reserved here. Okay, we ask for 6 bytes. The C developer asks for 6 bytes, but the compiler may reserve more than 6 bytes. Then there is the function called C library function called gets. Then after that, just return. Okay, so similar to the vulnerable function, the unsafe function we saw last week, which is string copy. Gets is also unsafe. So what gets does is it will read a line. Okay, a line ends with a 0. It reads a line, not only a 0. It also ends with a new line symbol. Okay, new line could be /n/a, not necessarily 0. There could, several characters could be a new line. So it will read a line from stdin. In our program, stdin is just the terminal. It will read it into the buffer pointed by the parameter. There is a parameter there. Then the problem is it doesn't verify how big is the buffer. It will just write things there. And the buffer, the input could be not much bigger than the buffer and leading to the overflow. So when you program, you should never use this function. This function has been there for decades. Modern compilers, if you use this program, modern compilers will tell you you should never use this program, use this function. Even if you read the C document, let's say we go to our server, we do a man gets. So this is an official document of this function, and you can see the description. It tells you, never use this function. This is an unsafe function, okay? It has been there for decades, but it's still there. No one is taking it out. So when you program, you should not use this. But this can demonstrate the vulnerability. Okay, so let's say why and how we can overwrite the return address and make it jump to the code we want the computer, the program to run. So in this case, our goal is still to get the flag, right? And we already know that in this address space, there is a function called print flag, right? The print flag function will just go to the file system, find the file, flag, read it, and output the result to us. So our goal is to somehow, we are going to call that function or execute that function, not necessarily call. So this is what the stack look like when we at the beginning of the vulnerable function. At the beginning of the C function, the stack pointer, ESP, points to the return address. Okay? So that return address actually points to somewhere in the main function, because the main function calls the vulnerable function. Then after that, the first instruction, let's skip that. It doesn't really do anything we need to know at this point. Then after that, we push EBP. So we save the EBP value The EBP was the main function frame. We save it on the stack. So ESP moves down. After that, we move ESP to EBP. So both of them points to here. After that, we subtract 18 in hex. So this block here represents 24 bytes, right? 18 in hex is 24 bytes. Yeah, this is hex. Then after that, there is another subtract to C. So C is what? 12? Okay. So here we have 36 bytes, something like that. Yeah. So you may ask why there are two subtract. Well, the compiler wise just add them together. Okay. Technically, if the compiler is smart enough, it can do that. But depends on the optimization level you are choosing when you compile the program. So anyway, this piece of program, it has two subtracts there. Then we have the call function here. This call function is called gets. We know gets has only one parameter, right? So there should be one push before that, before calling that function. So, and that is a push. So we know the push EAX. So we know that EAX actually has the address of the buffer because gets only has one parameter. That's the buffer where you store the input. Then we trace back. We do a reverse program. What is that called? Program slicing. In literature, that's called program slicing. So you say the call here, you say the push, then you say what is in EAX. So EAX is actually EBP minus E, which means EAX points to somewhere here. No, sorry. EAX points to here because this part is this point. Here is the EBP. So this point is actually EBP minus 18 in hex, right? So EBP minus E would be somewhere middle here, okay? So that is where the buffer is. Then we push this address here, then we call this function. So what happens in this function is, this is an unsafe function. We can overwrite everything. It will, where it will output the thing, your input. It will output into the buffer, which is here, EBP minus E. It can overwrite any address which is higher than here. Okay, we can overwrite part of this. We can overwrite save the EBP. We can overwrite return. Okay, let's assume here we are overwriting. Let's say if this is a safe operation, you are giving it a very small input. It's not going to overwrite anything. So after this, we are going to, the program will balance the stack. It will add ESP to 16 bytes. So ESP points to somewhere here. Move EAX, to move 0 to EAX because the return value is 0. EAX has a return value. After that, we have leave. Leave is equivalent to those two instructions. The first one is move EBP to ESP, then pop EBP. So after the first instruction, ESP and EBP, they point to the same location again, which is the saved EBP. Then we're going to do a pop. And what will happen to this pop? Pop will pop whatever is stored, whatever pointed by ESP to this register. And the register happens to be EBP. So what we're doing is trying to restore the saved EBP back to EBP, right? So after this, EBP will have the main functions stack frame address, which would be up there, actually. So I didn't draw it up there, so I just put it here. Then ESP will increment 4 bytes. So now ESP points to what? The return address again. Then we only have one more instruction to execute here, which is a return instruction. What the return instruction does is return instruction will take whatever is pointed by ESP, put that back to EIP, then ESP plus 4. That's it. Okay? So if this is vulnerable, if we are trying to attack this program, we're trying to exploit this. What we do is we overwrite whatever is here. We override whatever is the saved EBP. The value of saved EBP doesn't matter here. We're going to, you actually saw that because the key is overwrite the return address. You overwrite that to the address of print flag. Sorry, there's a typo there. Print flag, which is in the same address space, right? So after that, when you execute return, what happens is your program will jump to where? The program print flag. Then it will print out the flag for you. Even though after that, it will keep executing. It has a run EBP, so eventually the program will crash, but it will give you the flag. So let's take a look how this works. Which one is it? Return, overflow, return one. Okay, this one. Oh, someone solved it. Good. Okay. So let's say we do an object dump. We look at the program. We look at the vulnerable function, which is this, right? So the key here is you understand where the buffer is. The buffer is at EBP minus E, which means the buffer, at a C code level, we actually say the buffer is 6 bytes, remember, right? But you can say the compiler actually reserved the 12 bytes for it. E is 12, okay? That's why at C level, the value you get there is not reliable. Okay, so now, which means you need to override that buffer, okay? The buffer is 12 bytes. The value there doesn't matter. No one is going to use that. So after that buffer, another 4 bytes. What's that? It's a saved EBP, 4 bytes, right? We're not going to use it, so the value doesn't matter. So that's total 16 bytes. So after that, what we'll have? That's a return address. That's a lot of 4 bytes. And we want to override that to the address of print flag. And this program, it actually print out the address for you, okay? Print out the address for you, and doesn't change. If you run it multiple times, it doesn't change. So here is you can say, a lot of problems is the address doesn't change. So one way to protect this is to change the address. Every time you run this program, the address can change. So that's a protection called address-based layout randomization, which we will talk maybe in 3 weeks. But we will also say that even that protection we can bypass. We can still hack that. Okay, so what we do here is this program take input from std in, which means we just need to pipe the input to that. So we're going to print. So how do we construct our exploit? We said that first there are 16 bytes of technically garbage, right? We don't care what those 16 bytes is. 16 or 18? 16? Yeah. So after that, we should have 4 bytes of address, which is this one. So it will be 60, 62, 55, 56. So that's it. You can test. This is our exploit. We send our exploit to the program. It's not correct. What's wrong here? Let's say should be 18. So E is 14. Sorry, E is 14. So E is 14. So this one should be 18. Okay. So when we do 18, we get the flag, but because the EBP is changed, eventually it still triggers the segment fault. Okay. So here we see that we tried 16, didn't work. So what happens there? When we try 16, what happens there? Did we overwrite the return address? We did, right? We overwrite how many bytes of the return address? We actually overwrite the two bytes of the return address, right? So the lower 2 bytes of the return address, the higher 2 bytes of the return address stays the same. We didn't change it. But the lower 2 bytes, we changed it to this one, right? So it probably jumped into the middle of some random code. And that's why it triggers this segment fault. So if you want to debug that, we can actually debug that, right? To see what happens. Let's see how do we do this. We debug this. We debug this program. We want to give this output to it. I think this. Let's set a breakpoint on main. We run this program. I think the syntax is just this. I think that's a syntax. So this syntax will run this program, and the output of this program will go to the to be debugged program. So we run this. Let's see if it works. Okay, it works. Now we are in the main function. We can set up. We disassemble the main function. Let's just set a breakpoint here. Okay. Just set a breakpoint at the return. So let's say where it returned to. Oh, we should examine the stack first. Let's examine the stack. So right now we're at the beginning of the program, right? The function. So ESP right now points to the return address. Oh, are we supposed to go to val-foo? Sorry, we're supposed to go val-foo. Let's go to val-foo. Let's set a breakpoint at val-foo. Then we continue. Now we are in val-foo. Now the stack pointer, ESP, should point to the return address. So let's say, how do we do that? Because we are going to examine the memory, so we use exam, which is X. Then we just want to get a value. I will be okay, G will be okay, I guess. Then we just want to exam ESP, I guess. Oops, it's not a hex. We need a hex for that. Oh, we don't, yeah, so this is 32-bit, sorry. Should it be I? No. This is 32-bit program. It's actually here. I'm printing out 8 bytes. We only need 4 bytes. It's actually here. How do we print out 4 bytes? 4 bytes. W? Oh, yeah, W. Okay. So I'm printing out where ESP points to, okay? So ESP points to a return address. So the return address right now is 56556387. And let's look at where, let's zoom out a little bit. You can see that address, 6387, is actually the address after the call instruction, right? After the call, you make a function call, you're supposed to return to the next instruction, which is 6382. 87, okay? That's exactly what is here, okay? And we're going to override that. So we set another breakpoint. We set another breakpoint at the end of the val-foo. So when we get it here, the breakpoint 3, that return address is already overwritten. So we continue. Now we're about to execute return, but the stack is overwritten. We can verify that by executing the stack, the return address again, using the same command. And we can see that's what we get. 56005655, okay? We actually overwrite 3 bytes because the gets will append a 0 at the end, okay? We give 16 bytes. We override the lower half of those 4 bytes, which is, so we have 5655 there. Then gets append a 0. That's why we get a 0. So now the CPU is going to execute this one. So let's say we just let the CPU run. We do a SI, step in. See, now the CPU is in here. This is not a function, okay? We try to disassemble the function. GDB tells us this is not a function. Then it's, but we can still say CPU is going to execute that. Ooh, oh, it's actually not a valid address. It's not a valid address. We cannot disassemble the code there. So now you can imagine when we execute there, the CPU will retrieve code from that address, and that address is not backed. It's not mapped. So it will trigger the segment fault. It's not a valid address. So when we do SI here, we get the segment fault. Okay? So that is why that one, when we do 16 bytes, we cannot get the flag, but we get the segment fault. Any questions so far? Okay, good. Let's move forward. So this is what the exploit will look like. So this one, I actually give you the exact exploit. For some other examples, I'm not going to give you the exact exploit. I will just give you some high-level idea what the exploit should look like, and you need to construct the exploit by yourself. Of course, I mean, the video has everything. We record the class. Okay, the 64-bit version actually the same. The only difference is still you cannot trust the buffer is 6 bytes. You need to verify in binary code what the buffer is. Also, the saved EBP, it's not saved EBP anymore, it's saved RBP. So it's now 4 bytes, it's 8 bytes. The return address is not 4 bytes, it's 8 bytes. So let's look at it. Take a look at the 64-bit version. Return 64. .64-bit version, let's say, still overflow. So, where is the buffer? This is gets. Before we call gets, there is no push, right? Because 64-bit, we're not using stack to pass the parameter. So instead, we are using RDI to pass that, right? So RDI has a value which is EBP minus 6, okay? Same source code, 32-bit version you saw, compiler reserve 14 bytes there. 64-bit version, the compiler only reserve 6 bytes. That's what we ask for, right? So we have 6 bytes there. So the exploit should look like 6 bytes of garbage. No. Because saved RBP should also be garbage. So still 14 bytes of garbage. Also previous was 18 bytes. So let's say, so this one, what do we do? We need whatever. We need 14 bytes of garbage, 6 bytes the buffer itself, 8 bytes of saved EBP. Then after that we have the, oh, did we run the program? We didn't run the program. Okay, when you look at the program run, it outputs the address. So the address here is only 3 bytes. That's because the upper 5 bytes are 0, right? So we just need to add 0 there. Okay, so that's it. So we need D6, 11, 40, then just 0, 0, 0, 0, 0. That should work. Let's see. Yeah, it works. Right. So that is, so the same principle is just the size of registers are different, the size of address are different. So those are 2 very simple examples of how do you overwrite return address. Let's see a little bit more complicated cases. So we are going to, so the function we just returned to is called print flag, right? That function doesn't take any parameter. What if we want to return to a function which takes parameter and we want to give it a specific parameter? So how do we do that? So this is a slightly more complicated example. We have the main function. We have the val_foo. The val_foo is the same, okay, same as the last one. There is another function called print secret. In this one, we are not going to directly call print flag. We are not going to override the address directly to print flag. It works, but we're not trying to do that. We're trying to go to print secret function, and print secret will take argument, which is an integer in this case, I. If the I equals to this number, it will print flag. Otherwise, it will pity the fool. So if you have a challenge like this, there are many ways to solve this. First of all, you can directly, the val_foo, after val_foo here, you can jump to anywhere, right? You can jump to the function print flag. You can jump to the call to function print flag, right? All those two approaches will give you the flag, but that's not the purpose. The purpose, this one is, I want you guys to jump to the beginning of here, and to give that parameter. So how does this work? We have this stack here. We are at almost the end of val_foo. We have saved EBP, buffer, return address. The saved EBP points to somewhere in the main function, well, points to here actually. Print I pity the fool. So we overflow this one. We overflow it with some, let's say here, no one cares, just garbage. The saved EBP garbage. This return address, we put print secret here, okay? So now we return, what happens is we are going to jump to, let's do this step by step. Now we are going to, first is, we are going to move move EBP to ESP. So both of them points to here. Then we are going to pop EBP. Then pop EBP, then after that, EBP will have the value AAAA, okay? So we assume, we give garbage value AAA uppercase there. The EBP will have the value AAA, and ESP will points to this address. Then we're going to return. Then EBP stays the same. ESP will go up 4 bytes. EIP now will points to here, which is the address of print secret, right? Now we are actually in the print secret, okay? So previously, we are at the point of view of val_foo. Now let's switch the point of view. Now we are in print secret. Print secret, it doesn't know it was somehow diverted here by a buffer overflow. It is thought, it believes that it's called by some program, right? So it will have its own instructions like this. It will have push EBP, move ESP to EBP. That's the standard prologue, right? So what happens here is now we have EBP who has 4 A's. ESP points to, ESP actually points to here, okay? Here we have the old return address there. Now we have push EBP. Then EBP, the value, will move to the stack. So now we have 2 copies of 4 A's there, because that print secret will do that. Then we're going to move ESP to EBP, and both of them here. Then after that, we are going to check if the first argument equals to that value. So what is the first argument? That will be EBP plus, so EBP points to what? Saved EBP. EBP plus 4 will be return address. EBP plus 8 will be the first argument. So what happens is it will look for EBP, which is here, plus 8. It will think this address stores the first parameter. It will believe this address stores the return address. But actually we didn't set a return address there. We didn't do that. Okay? But the print secret function will believe that. It will think that way. So which means to override this one, this is what we are going to, we only have one shot to over that because the vulnerability is here, gets. So how are we going to have this exploit? We're going to have override the buffer. We're going to override the old saved EBP. Doesn't really matter what the value is. Then we need to have the address of print secret. This one is 4 bytes. This one, I'm not sure how big it is. This one 4 bytes. This one 4 bytes. Then the address of 4 bytes higher than the address of print secret, that will be considered as the return address used by the print secret, which we're not going to return from here anyway. So that address doesn't matter. What matters is the parameter here. Okay, that one should be set as this. Does that make sense? Okay, this one could be a little bit difficult to understand, but after more you do it by yourself, you can understand what's going on. So for this one, the exploit should look like this one. Oh, no, not this one, sorry. This one. Ooh. Oh, you solved it already? Good. Let's say, so we're still doing this. So let's go back to the slides. What's the size of this? Oh, I actually put it here. I don't want to show you that. Let's say, so the address here is E, which is 14, right? 14. So the buffer, this part is 14. This part is 4. So then we have 18 bytes. So it should look like 18 bytes of garbage there. Then after 18 bytes, we should have the address of the print secret. The print secret address is 4 bytes, which is 38, 63, 55, 56. Then after that, will be these 4 bytes. That will be the return value eventually returned by print secret. So we do not need it to return, so it doesn't matter. So that could be another 4 bytes of garbage. We just do 4x, right? Then after that, we're going to have the parameter, which should be what's that? Yeah, 1, 2, 3, 4. So it should be 1, 2, 3, 4, 5, 6, 7, 8. Okay, we pipe this into buffer, and we get a flag. So if we change this parameter, let's say instead of 1, 2, we say 2, 2, what will happen? So in that case, we are still going to the print secret function, but we cannot pass this test. So it should print out IP the full, right? So let's see if that's right. Oops. Okay. So in that case, we get IPT the full, and eventually we get a segment fault. The code I'm showing you here should not get a segment fault because I have an exit. I think I updated the code. I removed the exit 0 there. That's why If I do not have that exit, the exit is basically a system call. The system call tells the OS this program is going to quit. So there should be no segment fault. But without that, this function will return. And it's going to return to that random garbage address there. That will get a segment fault. I think I changed that. Let's see. No. Let me verify that. Otherwise, it doesn't make sense. It should be like that. Research code. So it should be overflow, return to, right? Here, we cancel main function. Yeah, you'll see that. The code we're actually running on the server doesn't have that x0. It's the code I have on my site has that x0. With that x0, it should not have that segment fault. Do you guys understand what's going on here? Okay, good. Okay, so, let's take a 10 minutes break. When we come back, there will be more complicated stuff. Yeah.
So, just for the simpler one right there, I was just having trouble understanding how this was determined, how many you need, and then also how the hex was determined.
So this one.
Yeah.
So you first need to understand here we're going to overwrite, right? Where is the buffer? Because your input is going to the buffer, and everything beyond the buffer. So where is the buffer? You need to read this code. So here is gets, right? So gets only has one parameter, and it's in RDI, and you can see RDI actually equals to RAX, and RAX is RBP minus 6. So which means the buffer is at RBP minus 6.
Okay.
So here, so we have you're looking at 64 bits, right? So this return address,
Yeah.
bytes. Right? After the return address, we have saved what you only have what the unsafe function gets. You only have a sequential override. It's not like you can skip this part and directly override here.
Okay.
Can't, right?
Yeah.
So that's why you need 6 bytes of garbage here.
Okay.
Another 8 bytes. So those 14 bytes, the value doesn't really matter. Whatever you give. So then you have 8 bytes of return address where you want to go to.
So by determining where the buffer is,
You need to rate this. You rated a disassembly
yeah,
code.
yeah. Okay. And then the hex is also.
So see here, so the A here, the A doesn't really matter, right? It can be anything.
Yeah.
It's just so here should be 14 bytes. After that will be 8 bytes of address, because this return address is 8 bytes. Yeah.
Okay. How do you know that this is like D61140?
That's because the program printed out for you.
Oh, so this is just equivalent to what the.
Yeah, the program, where is it? I print out it for you. Yeah.
Okay.
But of course, I mean, in real world hacks, they're not going to print this out
Right,
for you.
right,
But there are many ways to find out where it is. Yeah.
Okay.
But now we're just doing the simple things. Yeah.
Thank you.
Any other questions? Okay, so someone asked a very good question here. So it seems like the approach we use here only works for the 32-bit, doesn't work for the 64-bit, because we can only override the stack in this example. When we override the stack, we can override the return address, we can override save the EBP, we can also override the parameter, because the parameters are stored on stack. But in 64-bit version, the parameters are not stored on stack. They are directly passed in registers. So using this approach, we cannot override that. So that is absolutely correct. So to do a 64-bit version, we are going to use another technique. We call it return-oriented programming, which we'll cover at the second half of the class. It's a more advanced technique. It's one of the techniques that dominant all the attacks in real world right now. So when we talk about return-oriented programming, we will revisit these examples to say how we can hack those examples, the 64-bit version of those examples. Okay, then, well, so we saw example with one parameter. Then obviously we can extend this to multiple parameters. So we slightly change this print secret. It has two parameters now, I and j, and we compare both of them. So this is very simple because we know the parameters. They are together on the stack. So we will just override something like this. Okay. So this will be part of your homework. We're not going to show the demo of this. We will just skip this one. This is 3. Okay. So you see that we have been returning to one function. So can we return to multiple functions, which return to a chain of functions? If those functions do not have parameters, actually we can chain all of them together. There's an unlimited number of functions we can return to. You can see that originally the return address was here. The next return address will be here. Then the third return address will be here. So if we list all the return address just here, then we can return to all of them one by one, right? The first one will return to the second one will return to the third one. But they cannot have parameters. If they have parameters, then the address of the return address and the address of the parameter will overlap. So that obviously doesn't work. So let's go back to the example here. Let's say this is the epilogue of the vulnerable function valfoo. EBP points to save the EBP, and this one we just put some garbage there. Then the return address we put the function f1's address there. Then after valfoo returns, so this is actually after the epilogue. This will be at the beginning of f1. The stack will look like this. So for f1, ESP will points to 4 bytes higher. So which means at this address you can put f2's address there. Then after that you can put f3's address. So when you override this, you can just put function 1, you have the saved EBP, the first return address, you put f1, then 4 bytes higher, f2, f3. Then you can chain functions together, right? So one example, this works for, because this one we do not pass any parameter. It works for 32-bit and 64-bit. This is our vulnerable function, the valfoo, the same. Okay, buffer 6 bytes, gets. The main function print out the address of 5 functions here. And we are going to chain those functions. So each of those functions will just print a word. Knowledge is power. France is bacon, something like that, right? Oh, by the way, does anyone know France is bacon? No, France is bacon. No, if you don't know what that is, just Google France is bacon. Yeah, it's a funny story there. Okay. So what do we want to? We want to print out knowledge is power, France is bacon, by giving some malicious input to this program. So how do we do that? We just override the return address one by one, right? How many return addresses do we need there? 6. Here are 5 functions, but intentionally, I said knowledge is power, France is bacon, so we're going to return to those 5 functions 6 times in total. So one of the function is we're going to return it twice, okay? Twice to it. So let's go. This is return change 32. Let's run this program first. So we get the address of those functions. Then Python true. Print. Oh, we don't know how the size of the buffer, right? We need to take a look at the size of the buffer. It may be the same. Let's take a look. Yeah, it's the same. It's a still EBP minus E, so still 14 bytes there. So what we do is we put 14 bytes of, no, 18 bytes. 14 bytes plus the 4 bytes of saved EBP, 18 bytes there. Then we put the next return address here. So we want to return the address of knowledge. What is knowledge? Where is knowledge? Knowledge is the first one. So we put the 2D. We probably can put this value directly there. Let's see. Oh, when we do X, it doesn't work this way. So, yeah, let me do that the old way. 2D 625556. Okay. So when we do this, we are going to return to the first function. The first function will print out knowledge. Then it will return, but it has an invalid EBP value, so it will print out knowledge, then it will get a segment fault for us, right? Why it's not returning? What's wrong here? 2D 625556 looks correct to me. What I did wrong here? What did I do wrong here? Any idea? Okay, this part looks good. Did I calculate it wrong? Do I have a side there? Yeah, that's supposed to be correct. Interesting. Let me see. 2D 625556. Looks like we need to debug. I'm not sure what's going on actually. Any idea? No? Let me check the program again. This is ball foo. This is EBP minus E. That's right. E is 14. Plus 4 should be 18. Yeah. So this part obviously doesn't matter. I mean, okay. I didn't plan this, but looks like we need to debug what's going on here. To overflow, then we run this program. This is the input we're going to give. Now we are in overflow. We are in overflow. We're at the beginning, so we examine our ESP, which points to the return address. So this is the return address we have. It's 6328, which is we disassemble main. We should say 6328. We are here, right? That's the return address, which is after the call to overflow. Okay, that's correct. Now we disassemble again. Let's set a breakpoint here. So now I set a breakpoint at the end of overflow. We keep running. Now we are at the end of overflow. We should have the return address overwritten to this address, 2D62. If it's not, then something's wrong there. It's correct. 565562D2. Okay, that's weird. Then that's correct. So let's go to there. Oh, we're actually in here. Oh, I know what's going on. Okay. So you see, we actually jump to the function fi. Okay. So if we continue, it's supposed to print out. I think I know the problem. The problem probably is because, where is it? Okay. The problem is this print, there is no new line there. There is no, basically there's no new line. So the program didn't have a chance to really print out. The OS doesn't have a chance to really print out. The OS is still waiting for the program to give more. If we have a new line, maybe we do F5, it will print that out. Let's try F5 instead. So before the program had a chance to print out, the program is already dead. So let's try F5, which is A1. Yeah, see? So if we do F5, it actually print out a bacon, okay? So if we change this back to knowledge, so here would be 2D. So we're going to knowledge is power. So the second one we're going to print out is which is 4A 625556. So after that, we print out power, which is F3. F3 is 67625556. So that's knowledge is power. Then we print out frass is bacon. Frass is F4, which is 84, 62, 55, 56. Then we're going to print out the is again, which is this part. Right? We just copy this. Copy it here. Then the last one, we just print out the bacon, which is 81, 62, 55, 56. Okay, this should work. This should print out the whole thing for us. Okay, you see? When we do this, we chain 6 functions together. We print out knowledge is power, frass is bacon, and this is printed out by the third function, F3, which is, I would say, returned to twice. We didn't really call that. We returned to it twice. Okay, so you can see we can chain functions together. But if those functions have parameters, it will be more challenging. That's because the return address is supposed to be here, but the argument will have the same address, so they overlap. Unless the return address and the argument has the same value, you cannot chain them together, right? Okay, so now we are moving to the really interesting parts. Is in the previous example, in the address space of the program, there is a function called print flag. So you only need to go to that function, and it will return a flag to you. So in real world, the program will not have a function to help you do something like that, right? So you need to inject your shellcode into that address space. The shellcode here, I mean something to do something malicious. For example, print out the flag is a malicious behavior. So why would that program, a Beeline program, has a malicious function for you to return to? It doesn't have. So you can inject the malicious program there, and that program, we call it shellcode, because traditionally, it returns a shell to us. Give us a shell, we can do anything with that. So we are going to, so some shellcode, but obviously now a lot of shellcode doesn't really return a shell. It's maybe just read the file, print out the file, or send out the file. But we still call them shellcode, okay? So there are several questions we need to answer before we look at how can we inject and return to shellcode. The first one is, obviously, we need to overwrite a code pointer. And that code pointer, at some point, will be executed by the CPU. And that code pointer could be a return address on the stack. And to overwrite that, we need to overwrite enough data to overwrite that. Then, what do we overwrite the return address? If we return to some random address, then the CPU will jump to some random address and crash the program. We do not get what we want. So we want to return it to something like a print flag or our own code, okay? Our own shellcode. So what should our shellcode look like, okay? So actually you already saw that last week, but today we're going to look in depth what does that look like. So here is the vulnerable function, and it has a buffer we can overwrite. We can overwrite the safety EBP and return. Our goal is to override this to point to our malicious code. So in this example, where do we put the malicious code? Let's say we only have one shot. We can't give the program some input. So the malicious code should be part of that malicious input, right? The malicious code will be that. So we can put the malicious code at the beginning of the buffer. We can put the shellcode in the buffer if the buffer is big enough. But in the previous two examples, the buffer is only 6 bytes or 14 bytes. They are not big enough to put the shellcode. But we can override everything above that. So we do not have to put the shellcode there. We can put the shellcode to some higher address. Okay? Another challenge here is we need to change the return address and let it points to our shellcode so it can execute our shellcode. The big challenge here is how do we know the shellcode's address? This is a stack. Stack is dynamic. Every time you run the program, it could be a little bit different, right? It's not determined at compile time. It's hard to find the exact shellcode address. Imagine this is a piece of shellcode. It could have 20 bytes. If you jump to the middle of the shellcode, obviously you're not going to get what you want, right? You probably will trigger a segment fault. So what we usually do is we add a lot of loop operations. So basically there are still instructions, but those instructions do not do anything useful. It will just execute the instruction, don't do anything, then pass to the next instruction. It will not have any good or bad results of those instructions. So if we can append a lot of those instructions at the beginning of our shellcode, that becomes a sled, right? And if we jump to any part of that sled, it will eventually give control to our shellcode. Does that make sense? So the shellcode itself could be small, 20 bytes, 25 bytes. The sled could be huge. So we only need to guess where that sled is. We just need to jump to the middle of the sled, okay? So we don't need to know exact location of the shellcode. So, so next we are going to look at real shellcode, only 28 bytes. We actually looked at part of this last week. Today we are going to see the details, and we are going to use this shellcode to crack a program not on our server, but on another online hacking platform. Okay, so this is our shellcode. The first thing you probably notice is there are 2 int instructions. In the background part, I said that's a system call. Int 80 is a system call. And this shellcode is making 2 system calls. It's a little bit weird. Why do we need 2 system calls? Because what we really want is to do this execve system call to execute a new program. Why do we have 2? Yeah, let's figure it out. So first, our goal is to execute. So there is a vulnerable program we're trying to hack. We're trying to replace that vulnerable program to to bin sh, which is a shell program. And to do that, we are going to execute the system call execve. Okay? So if you look at the system call table, you will see that we are going to do this one. Okay? So EAX should be 11. EBX should point to, this one is actually not the correct one. Anyway, this one is correct. EBX should point to an array of strings. The first one is the strings address. The second one is 0. EDX just 0. ECX very similar to the first one. EAX should be 11. So then let's look at this piece of code. We actually looked at the first half last week. So the first instruction, exclusive OR EAX, we get a 0 into EAX. After this instruction, EAX has the register has a value 0. After that, we push EAX. So EAX is 4 bytes. So we're actually pushing 4 bytes onto the stack. Now we have 4 zeros onto the stack. What we really need is 1 0, but whatever. We put 4 0 there. Now we push those 2 weird things there. So those are actually, so will be this order. We first push 86, 73. So 86 will be higher address. Will be at a higher address. So this is going up is high, going right is high. So it will be this order. Then we push the 12 bytes onto the stack. You may want to figure out what are those 12 bytes. You just go to the ASCII table. Then we have, let's say, we have where do we start? Yeah, we start from here. 2F, 62, 69, 6E, 2F, 2F, 63, 68. Okay, that's the order. So if we put that order here, the 8 bytes, then we go to the ASCII table. We find we're actually pushing /bin//sh there. Like I said, the 2 slashes don't really matter. That's the same as 1 slash. You can actually put 2 slashes here and remove 1 slash here. Doesn't matter. That's the same thing. Now you can see that what we actually put here is a string. That's a C string /bin//sh. That's the name of the program we are going to execute. That's a shell. Now, since this is a push, the ESP points to here. Then we move ESP to EBX. Now EBX also points to here. EBX points to this string now. Then EAX is still 0. We move EAX to ECX. So ECX is 0. We move EAX to EDX. So EDX is 0. Sorry, it's jumping there. What's going on? It should not jump. Anyway, then we move B, which is 11 to AX. Then we make the system call EXE save AE. Okay? So there is only one class, one session. In the Shellcode session, you are going to write something like this. In most of the cases, you can directly copy this just to use in this class. You do not need to write a byte to byte of the Shellcode. You just use them. Okay. So now we make the system call EXE save AE. So what happens after this instruction? What? Sorry, I cannot hear you.
The new process will be a child process.
No.
A new shell.
The share program will replace current program, but there is no fork, so no new process is created. Okay, yeah. So now we will have it's still the same process, but it's not the same program anymore. The old program is replaced by the bin sh, but that is when this operation is successful. What if this operation is not successful? The system call may return say, hey, you don't have the privilege to do this, or whatever reason it cannot find this program. So this instruction will not replace the current program. So in that case, what happens? In that case, so if in a successful case, the whole program is replaced. So we never have chance to execute the rest of those three instructions, right? Because we have a new program. This program doesn't exist anymore. But if this is not successful, it will return here. And if we do not have the last three instructions, there will be some garbage instructions here. Then what will happen? The system will crash. The program will crash. If the program crash, as an attacker, you leave some trace there, right? So you will leave some trace. Hey, the program crashed. The user may identify something is wrong. That's why we add 3 more instructions here, and those 3 instructions will only be executed if here this instruction is not successful. Then those 3 instructions, what do? We get EAX to 0 again. Then we increase EAX, which means EAX will be 1. Then we just call the system call. That's it. Okay? So after this system call, if it returns, it will return why the system call is not correct, why the system call was not performed. And the return value will be EAX, but we don't care. Okay? As an attacker, we don't care. So, and the system call we are going to call is exit. So by doing this, the program will not crash. It will exit gracefully. So technically, this Shellcode can be even smaller. We do not need the last 3 instructions, which will be, because this here is 80, so you can identify this is 80. CD80 is that system call. So those 5 bytes, technically, we don't need that. So technically, this can be even smaller, 23 bytes of Shellcode. Okay, now we are going to hack a program on this server. There is a war game server called Over the Wire. They have all kinds of hacking challenges at different levels. We are going to hack this level, Behemoth's level 1. So what we can do is we will SSH in. The reason we're not doing this on our server is a latest version of Ubuntu. When it returns the share to you, it will not be a privileged share. So in our server, we are going to write a different share code next week, which will read the file, output the file, but do not really replace the program with a share program. Okay, so we will log in this server. This is my local version. I just go, let me make the screen a little bit bigger. Okay, let's log in the server. We need a password. I already gave you the password here. Did I click that? Okay, we are logged in. So this, we can go to the behemoths. Okay, let me explain a little bit how this system works. This system is similar to our server. There are many different vulnerable programs, and each of the program is a set UID program. But those set UID programs, they do not belong to the root. In our server, it belongs to the root, so it can read the flag. In their set UID program, for example, the program behemoth 0 belongs to the user behemoth 1. And the behemoth 1 can read its own password. So if you hacked behemoth 0, you will be able to read behemoth 1's password. Then you log in as behemoth 1 and try to hack behemoth 1 and try to find the password of behemoth 2. That's how it works. Okay, so the program we are going to hack now is behemoth 1. So this is a program we never run, right? So how do we do it? We run the program and get a feeling what it does. So this program asks for a password, right? So we just guess this is a password, okay? So you may think since it asks for a password, then the password is probably stored in the binary. Then we can extract the password, right? Maybe the password is encrypted, then we can still decrypt the password. So let's do an error trace of this program again. Oops. You can say the error trace doesn't give us much information there. The program will call the main function, obviously, then it will call printf to print out the string password to ask you for password. Then it will call gets. Okay, hey, gets, that's an unsafe function. Now after that, it will call puts. The puts, same as printf. It will print out authentication failure, sorry, that's it. Okay, so let's do an error trace to say what kind of system call it makes. The system, then let's just put them here. The system call here, there is something very interesting here. Let's say if someone can identify that. There are some standard system call like write that maps to the puts. There is read that maps to the gets. And there is a break that's just to, the program is setting up its heap or whatever. So, but what is interesting? What is this one? Get random, right? So that's a system call. So we do a get random. That's a system call to give us some random bytes, some random value. So this program will compare your inputted password with some random value it gets at runtime. So what is the chance you can guess the right password? Right? What? Sorry, I can't hear.
The seed doesn't change.
The seed is probably, the seed doesn't have to be I don't think the seed is need to be a system call. Yeah, so what you are talking about is a C library function, right? The C library, what you do is you get a seed, then you call random. The seed doesn't have to be a system call because the seed can be anything. But the random is a system call, yeah. Yeah, I'm not sure if the seed is a system call. I think maybe not, but get random is a system call because you need a kernel to generate a random number. Okay? So the chance for you to guess that, for example, this time it's a 4 bytes of random number. It's 10 to say 2, say 2. If we run it again, it will get a different random number. Where is it? Okay, it's different. Every time you run this, will be different, right? So obviously, if you want to guess the password, brute force the password, or extract password from here, that makes sense. So you have to use software vulnerability, okay? The technique we just learned to crack this program, okay? Then now we get a feeling how this program works. We have no choice but disassemble this program. What's that? Behemoths. What? When we look, oops, should I, which, that should be. Probably we're looking at the main function. Yeah, I think we're looking at the main function. What's going on? The main function. Okay, this is the main function here. It's a very small main function. Looks like our vulnerable valve there. The main function calls gets. Okay? The gets will put your input to the buffer. The buffer is at EBP minus 43 hex. Okay, so which means we can overwrite that. So let's say, so the stack will look like this. This is a stack of the. This is a main function. It's a main function. Oops. Stack. This is high address. This is no address. Let's assume return address is here. This is a 32-bit program, so return address is 4 bytes. Then save the EBP 4 bytes. Then where's our buffer? EBP minus 43, right? So EBP minus 43. 43, what is 43? 67? Yeah, I think it's 67, right? So 43 is 67. Let's assume it's here, okay? So this part is 43 in hex or 67 bytes, okay? Then after this, we have 4 bytes, then we have the return address. So we're going to use our approach to inject our shellcode. Our shellcode is at least how many? 23 bytes. So the example I show you is 28 bytes, but we can remove the last 5 bytes, so we can have 23 bytes. So the problem here is we don't know the exact address here, okay? We can debug this. Let's say we debug this. We use GDB. Oops, what's going on? We debug this program. We set a breakpoint on main. At the beginning, we print out where ESP is. Oh, we're not running, sorry. We should run this program. Now we print out where ESP is. So ESP will be D4, say4. So when we run this program, ESP will be FF D4, say4, okay? But this is the stack when we debug this program, when we run this program inside GDB. If we run this program outside GDB, it will have a different stack. Because imagine how GDB works. GDB is a debugger. You give GDB the program you want to debug. GDB will set a lot of information on the stack, then create the new process there. So the stack will be different from what you just run that program. The stack will be a little bit lower than that, actually, because GDB will push several hundreds of bytes onto the stack. We don't know how many. Different version of GDB would be different, okay? So, but we know it probably will be some address higher than this. Probably some address higher than this one, okay? Then let's say, then how do we do this? We can put the shellcode here. We put 30, so the whole thing is 67 bytes. We put shellcode 23 bytes of shellcode here. That's our shellcode. We can actually even put my shellcode here. So that gives us a little bit more. So the whole thing will be 71. We can put our 23 bytes of shellcode here. That will give us like 48 bytes of NOP sled, right? We can put a NOP here, 48 bytes of NOP. Then we put the address here. Then we start guessing the address from here, maybe a little bit higher, something like that. Make sense? Okay, so let's try that. What is our shellcode again? I think I put the shellcode somewhere. Oh, yeah, I put it here. So let's use this approach first. Then we try an even better approach after this. No, I need a text editor here. I don't have another terminal. Yeah, I just need a gedit, I guess. Because I copied this, I need to remove those things. Okay, so here, so C0. That's correct. So what we need is, so here I'm trying to construct so we put 48 bytes of NOPs. NOPs could be 80. There is actually in instruction NOP in x86 instruction set. So this is instruction. This instruction doesn't do anything, and it has a hex value of 90. It's just 1 byte, so we can use that. Obviously, some other instructions can be equivalent to NOP if we can use those as well. So here, let's say we have 90, then we want how many bytes of that? 48 bytes of those. Then we should have 4 bytes of address. Then we start guessing from that address we get from GDB, but we know that address is probably too low, but we can start from there. D4, FF. Then after that, we put the shellcode. I should put shellcode before that. So this shellcode is actually too long. This is 28 bytes of shellcode. This is 28 bytes, so we need to remove the last 5 bytes. 1, 2, 3, 4, 5. Okay, so now it should be good. 48, 23, that covers 71 here. Then we have 4 bytes of return address. Then we're good to go. Let's see. Let's try this. We put this there. Let's run this program. Nope. It's authentication failure, and we didn't even trigger segment fault. Oh, we did trigger a segment fault. The reason is I added a cat at the end, so that didn't show us the segment fault. Okay, so what should we do? From here, what should we do? we should keep guessing, right? We know this address is probably too low. We increase it. Then let's guess. Let's keep guessing. We should, oh no, not this one. We change this address. So our knob sled is only 48 bytes. So we probably do not want to jump too far. Maybe say from C to E. That's how we guess. And no. F. No. So after F, we need to go up. Then, so D4 may go to D5, then 1, 0, something like that. Okay? We already guessed 5 times. No knocks here. But you can see that if we keep guessing, if we write a script to keep guessing like that, eventually we're going to hit that, right? However, let's think a more effective way to do this. So the reason I want to show you this is it will work, but it's not effective. So look at this picture here. How we can increase the chance of our guess rate? The goal is to have a huge knob sled. That's the goal, right? So what we can do is, instead of put the shellcode here, when we put the shellcode here, we have at most 48 bytes of knob sled, right? That's because gets start writing from here. We put the shellcode here, then we only have 48 bytes. But from here to here, we have a huge room, okay? Why do we have to put the shellcode here? Let's maybe put the shellcode here, then we put the knob at here, then everything here, we don't care. We don't care what is there. We, instead of point the return address from here to here, we point the return address from here to here, okay? So now we can have a huge sled, let's say. Now, how do we write this? So first, we need to fill this whole thing, which is 71 bytes. And it can be 71 bytes of anything. So we just use that 91, doesn't matter. Then after that, we have the return address there. Then, what did I do? So we remove this part. We remove this part, then we put the return address there. Then we put the shellcode here. So before the shellcode, we put a huge sled. A sled has to be a knob sled. So let's do okay, let's try 2,000 bytes. Previously, we only have, like what? 48 bytes. Now we can go to huge. Let's say 2,000 bytes. Let's try. Nope, doesn't work. We increase this address, so we have D5. Now we can increase a lot. We can increase to D6 or even bigger. We can increase to a bigger address. Let's say, because our knob sled is huge, this one we directly increase to, let's say, DA. Still no?
You got some syntax error at the beginning of the command.
Where?
So the /x90 times 70.
Oh, yeah. So that, okay, yes. Yeah, good catch there.
And /71 times 71.
Which one?
So instead of /x90 times 70. On the left.
This one is correct.
Oh, the previous one. The previous x90 times 71.
Yeah, this now is correct. I add an X there.
Yeah, but times 71, not times
Oh, 71. Oh, why did I do 7 there? That's weird. Oh, good catch. Okay. Okay, actually works, see? Because we have a huge sled. Now we have 2,000 bytes of sled, 71. Now, when we log in, we were behemoth 0. No, we were... Eh, why? We should be, because this is setuid program, right? So should we be behemoth? Let's see. Can we cat? Our goal is to get the password of what's the password's address? Let me see. Is this address? But you see that right now we have a shell, right? First of all, you see we have a shell. We can. Oh, this one probably cannot. I'm not sure if we can copy. Oh, we can. Yeah, we don't have a permission. We have the shell, but somehow we are not getting the password. What's going on? So when we get shell, when I do who am I, we should be 2, not 1. We did get the shell. This one is correct. Let's see. Grab behemoth 1. This here. That part is correct. So here we have all the password. You can see, yeah, we have to be behemoth 2, and the program we are executing is this one, and it belongs to this guy. Unless they also changed it, so unless they update it, so it's same like our server now. Let me check if it's a. So what should I do? So this is also probably that's a problem. This is also a very new Ubuntu. Well, it worked last semester. Sorry, maybe they updated. Let me see. Here everything looks great. Got the share. Let me try to go to behemoth. The next behemoth. Should be. Let me try to go to behemoth 0 to see if that one has the same password there. So we go to behemoth 0. That's the first level. The password is just a behemoth 0. So now we run the program. Behemoth. We run the program. Behemoth 0. It asks for a password, but this one we can do an error trace to say behemoth 0. And you can see this level is only comparing your input to eat my shorts. So you just need to do behemoth 0 eat my shorts. Oh, sorry. So now I should input. Oh, see? Then it gives us a shell, which is a root shell. So this one we can't count the password. So now we can count the, oops. So behemoths, what's, so this one does give us a shell. Oops, I should do what? Okay, this one does give us, so this is a password I gave you guys to log in that. So when we log in, so somehow we get the share, but why the share we get is not privileged? That's weird. Let's try this again. We go here, we get the password on this. Oh, I didn't save that, right? Oh, we have to do this again. Oops. Let me do it here. So first is 71. Now we can have the whole thing, doesn't matter. So this is the address. This is the address. We use the A before, and it's just go to A. Then we add another 2,000 bytes of SNAT. Then the share code. That's a full share code with that exit there. Then we go here, say. Ooh, there's a syntax error somewhere. Print 2000. You guys say where is the syntax error? Okay, this part looks good. But we need a cat there, that's why I put a cat there. Okay, this one looks good. Oh, it's probably because the program is not here. Oh yeah, program is not here. We are not out of that folder. Behemoths 1, okay. It does give us the shell here. Oh, no, not this time. So this time the address will be a little bit different. Let's add it even bigger. 71 address. Previously we had the shell, now we don't have the shell anymore. So it was D4. Okay, let's go to that folder, then we will have the same, almost the same stack there. Then we do this again, change to this one. So previously we were using A there. Nope, not even A is not working. Let's do E. Our share code is wrong? No, it looks like the same share code. There is a 80. Oh, this is a. Oh, I already deleted those 5 bytes actually. So this is a 23 byte share code here. So let's debug this again. GDB. D4C4, it's not changed. They didn't enable address space layout randomization here. So D4C4, that's a very small address, so it cannot work this way. That makes sense. 6, that's 200 bytes. No. D9. Now we cannot get a shell. We got a shell before. What's wrong? Why we're not getting a shell? We were using A there. We got a shell. We didn't have a privileged shell, but we have a shell. Did I do anything wrong? 71 looks good there. That's an address. Then that's mobslet, Shellcode, and our mobslet is huge enough that it's huge. Maybe it's too big. Interesting. Use a smaller one, just D5, let's say. It's not giving us shell. This one is 90, doesn't matter. C4, D5, F, A. Oh. What I'm doing. Okay, this is not a lobslet. Why? What I'm doing, this is not a lobslet. This one cannot be A. If it's A, we jump into A, which is not a valid instruction. So this one has to be 90 here. Yeah. Okay, sorry about that. Okay, now we do here. Okay, we do get a shell, okay? We do get a shell, but it doesn't look like a privileged shell. I don't know why it's not giving us a privileged shell. We do get a shell. I think they probably updated the system. So what happens is we cannot get a privileged shell. So we have to use the approach that we use on our server, which is our shellcode is not going to give us a shell. Instead, our shellcode will read the file and output the file. If it get a shell, it will create a new process, and the new process will not inherit that setUID privilege. So you can say, basically here what we do is we create a new process, which is being.sh. But this being.sh still has a privilege of behemoth 1, not behemoth 2, okay? So if we do not create a new process, in that behemoth 2 process, in that behemoth 1 process, we directly read the file and output the file that should give us the password. Okay, but I didn't plan to cover that this class actually. Sorry about that. I promise you, this guy works last semester. They did update this. They even updated the password. I noticed that today they updated the password. I think probably the reason is not last semester I asked everyone to do this, so kind of like we DDoSed them. So yeah, because we did that in the class, so we kind of DDoSed them. Then they probably figured something's wrong. Then they updated their Ubuntu, and because they updated the Ubuntu, now the old exploit doesn't work anymore. Okay, sorry about that. Okay, I promise next week I show you how we get this one. Okay. Okay, anyway, we still have like 15 minutes. So next, I Also, I need to update the homework, obviously, because of this. It's good that we find this out in the class. Okay, so next, we still have like 50 minutes. Please try to exploit this program, overflow local 3. Start with 32-bit version, and then move to the 64-bit version. This one is a little bit more difficult than what I showed you guys in the class. This is what I designed last semester for the midterm, and I believe only 2 or 4 students got it. So I probably made it too difficult. So this year I'm moving this to the homework and in-class exercise. Okay, yeah. Overflow local 3. Okay, no source code, just the binary code. So when you run this program, it asks for some input. Oh, it asks for 2 inputs, or could be more. Then it will give you some hints. Okay. give you guys a little bit hint here. So when you run this program, you already get a feeling that the program is looking for, oops, let's go. When you run this program, you get a feeling the program takes what? 2 inputs, right? Or it can be more. It can be 4 inputs. It's actually taking a specific length of input. Then you go to not really 2 or 4. It has to be some specific length. Then if you disassemble this code, what do you look for? You first look for the print flag function, because you want this program to somehow call print flag. And this is where it is. It calls print flag here. So you want the control flow eventually reach here. So before this, there is a jump. So jump what? Jump not equal. If it's jump, before that there is a compare. So it will compare EAX with a hard-coded value. So if they do not match, they are not equal, it will jump away to some other place. If they match, it will call print flag. So what are your input? It will go through some kind of calculation. Then the calculation result will be in EAX. And that result will be compared with this hard-coded value. That's it. So also it gives you some hint, right? It gives you some hint. It gives you I times J, this value. Okay, look, you can try, you can. I times J. What if, let's say, we input 1, 2, no, it has to be, how do we do that? Let's say, no, I think that's enough. Okay, I'll leave it to you guys for about 20 minutes. who solved it so far? Okay, let's say a little bit more information for you guys. First of all, this function is called evolve, right? So I'm telling you this is a vulnerable function. Then why this is vulnerable? Because there is an F rate. If you just check the document of F rate, you say that's same as gets or what was the other one we were using before? String copy, right? So either it's an unsafe function, introduce buffer overflow there. Then you check where this F rates put things. It will put at EBP minus 20 in hex, which is 32. Then you can imagine that, let's say, this will be the buffer, and this will be save the EBP, then there will be 32 bytes between the buffer, the beginning of the buffer, and the save the EBP. Then you go to that print flag, and you find out this one actually compares. Those are the three instructions here. It will take the value at EBP minus C. So this is obviously a location that you can overwrite by writing to EBP minus 20 because it's a higher address than EBP minus 20. It will put that value into EAX. Then there is an instruction called IMUL. That is integer multiplication. So it will multiply that value with another value at EBP minus 10. So this one is 16, C is 12. So basically 2 integers, both 4 bytes, and you can overwrite them with that F rate. Then those 2 values, if they multiply them together, it has to equal to this. How can you get 2 integer values? Their multiplication is this one, and you need to overwrite to those 2 addresses. Okay. So 2 steps. You need to figure out what you need to overwrite, and you need to figure out where you need to overwrite. And also, you cannot overwrite the return address here because you say the F rate, you are going to read 18 in hex, which is 24 bytes. So F rate will only read 24 bytes, but the buffer is at EBP minus 32. So you are not going to overwrite. You do not have a chance to overwrite the saved EBP or the return address. You can only overwrite things before that. So if you are trying to overwrite the return address, that's not the correct direction. how the stack looks like. You are overwriting from EEP minus 32. This is what F3 does. Then after that, there will be two integers, EEP minus 3 and EEP minus 10. Those two will be this one times this one equals to that hard coding value. So how many bytes you need here to fill this buffer and override those two, and what you should give you a little bit more hint here. So if I input something like this, A16, then I put 8 bytes here. So the first 4 bytes will be 1000, which is basically the integer 1. The second 4 bytes will also be the same thing. So I'm basically timing them together. So when I do this, I get 1. Okay? I times j is 1. So if I do, let's change this to 5 and 5. And what do we have? 25. Okay? So that's a hint I give you. I will copy this part and paste in our Slack.